Okay, thank you for having me in this session. I'm going to present the durability-based design of UHPC structures, a performance-based approach based on extensive laboratory research and long-term in situ observation. I'm a PhD student at Politecnico di Milano, and with the help of my colleague Marco De Voglio and Simona Di Cembra, and also with the supervision of Professor Librato Ferrara. I think he's hearing us from the room now. I'm going to present some activities which are within the framework of the project ReSHEAlience, which is funded by the European Horizon 2020. And the main objective of the project is to develop an ultra-high durability concrete in a cracked state, and also under aggressive exposure. Okay, so the main objective of the research I'm presenting here is to develop a durability-based design, namely performance-based approach, which depends on laboratory investigation and also the full-scale structural validation. So we will use both these inputs to feed up our proposed design methodology. I will be a little bit quick on presenting some results because I have some quite many slides. So the first one is the pilot that we developed in Italy, particularly in Tuscany. So it is a geothermal in the planet of geothermal water power plant. You see here the basin consists of 3 different containers. The first one is 10 centimeter ordinary reinforced concrete. The second one is 6 centimeter UHPC, only UHPC without reinforcement. The third one is only 3 centimeter precast UHPC. Then they stiffened with 20 by 20 UHDC columns. In this case, we are presenting different structural concepts with different material just to verify the use of a UHPC with compared to ordinary reinforced concrete. Also to give let's say a methodology to deal with this material. So you see here, like we have vertical and horizontal casting. We will go over this in particularly. Upon entering the basin, its surface life, we did some monitoring and measurements. You can see here, we are doing the displacement water measurement. So we filled this basin by basin, up to 1 meter and 30 centimeter, which is the surface level of each basin. Then we measure the displacement at the middle of the wall of each wall and at the quarter of each wall. But for the third basin, which is the precast and stiffened with the columns, we do 2 schemes of measurements. We call them the global one, which are distributed on 2 slabs and 1 column in between them, and the local one, where all the measurements are projected in 1 slab. Here I'm representing the results of the first basin, the ordinary reinforced concrete basin. The first 2 from the left are the side measurements, and the last one is the middle measurements. You can see here the line with the red one is a model of elastic model of finite element. We are just putting it there just to compare it with the measurements, the on-site measurements. Also, you see the curves as the water filling each basin from 0 to 100% of the surface capacity, which is 1 meter and 30 centimeter in length and height. Sorry. So we see pretty much good behavior in terms of displacement, and it's aligned with the predicted one, finite element modeling. However, for the middle one, we see a little bit of deviation from the model, and we think we will see later the shrinkage cracks in the base of the first basin, ordinary reinforced concrete. For the second one, we see, which is the UHPC, 6 centimeter UHPC, we also see a pretty much good behavior aligning with the finite element model. The last basin, which is the 3 centimeter, we see the global and the local. The first one is the local one, and the second one is the global one. We also see a good prediction compare. We saw also the second effect in the middle. You see the displacement in the middle of the base or of the panel is more than the top, which is the effect of the second effect of the panel. Also, you can see the column, which is stiffened, the two slabs, adjacent slab, they have maximum displacement of just 0.1 millimeter. So it's very, very minimal, and that's what stiffening the whole basin globally. Then we did some strain measurements for the first basin. We put the strain in the steel rebar in the construction phase. Then after the construction phase finished, we put some strain gauges on the concrete faces for the second and the third basin. We see here some measurements of the strain. I will just comment the UHPC surface strain. You will see here the vertical one, V, and the horizontal one, HA. The vertical one is reading more, 0.003 strain measurements. The horizontal one is less. For the third one, since we are reducing the thickness of the wall, we are absorbing more strain. However, the displacement we saw is very minimal, so we will comment on this later also. We did some numerical analysis, nonlinear analytical model. We're trying to figure it out, but just keep in mind the model just for a cantilever wall. So we didn't account for the second effect. That's why we see some deviation, but just we are trying to capture some behavior. Then moving to the constructability of the UHPC on pilots, since we have two different methods, we have cast in place and precast element. The second basin, W7 and E7, they are cast in place. And you can see here, we did non-destructive measurement of the fiber dispersion by magnetic tool, magnetic sensor. So we survey all the wall, W7. You can see here the blue one is indicating the lack of steel fiber. The red one is indicating of the normal steel fiber, the designed one. And you see here also, you can see the point where the casting was displaying. However, for the last basin, the precast one, we see homogeneous, let's say, homogeneous distribution of the steel fiber. We will comment on the second basin later also. Here we see for the first basin, we encounter some restraint shrinkage in the base on the three walls. But we put in the ordinary reinforcement some crystalline admixture to heal the cracks. So they healed after, let's say, 3 or 6 months after the surface life. In the beginning, they have a little bit of leakage. The second basin, I'm here coming back to the steel fiber surveying that we investigated earlier. We see here that the lack of steel fiber at the top jeopardized the top layer to have some shrinkage cracks. And we went back to the laboratory. We did the strain shrinkage, the ring test to see if these cracks are due to the restraint, the autogenous shrinkage. We put three patches, one without steel fibers. On the left, we see after 14 hours and after reaching 15 microstrain, the crack occurred without steel fiber. However, for half and full amount of steel fiber, after reaching 100 microstrain, no crack occurred. So we had to stop the test. And you see, like here, we stopped this test because it has a full amount of fiber. So we were afraid that it will not come out of the ring test, and the technician were afraid, so I cut it over. This is some durability observation. We did some periodic assessment every month to go there, and for 3 full days of measurements, and we did the displacement and also the strain gauges, and also observation of crack width. And here is some, you see here 6 centimeter UHPC wall after about 2 years of surface life, and the 10 centimeter ordinary reinforced concrete wall. You see the leaching started on the ordinary reinforced concrete. Also, on the right side, you see when we first filled the first tank, we see some leakage of the restrained shrinkage. However, for the second basin, the 6 centimeter UHPC, we saw some micro crack. We went there with a microscope. We didn't see the crack, but maybe this is just a micro crack with some picking moisture from the filling of the tank. I have to remind you here that this water is geothermal water, so it's containing chloride and sulfate material. Then that was on-site measurements. Now we went back to the laboratory, and we took some specimens casted during the construction of the basin. We took here 6 1.6 meter by 1.5 meter slabs. We surveyed them for the steel fiber. We saw that they have a pretty much good steel fiber distribution. And then we cut them to, like, each slab produce 41, 43, depending on the exact dimension, 41 specimens of 0.5 meter, 10 centimeter, and 3 centimeter thickness. We did here some analytical or statistical investigation relating to the magnetic survey. You see on the right, to the exact amount of the steel fiber in the design mix. We saw that the magenta line are the designed one, and all the slabs are within this range. Then we went to the laboratory. We did some sustained load setup. So we first we used the flexural the resonant and the UPV test as a proxy for the durability indication. Then so we did this before the pre-cracking. Then we induced some damage to the specimen. I will show you later the exact procedure. Then we evaluate them after the pre-cracking. Then we put them in the exposure. Then after a periodic or interval time, we took some specimen, evaluate them again. Then we did the mechanical test at the end. So the aim is to link the durability and the mechanical behavior together over time. This is the pre-cracking curve for each slab. So each slab contains like 41 specimens. This is the pre-cracking curves. The idea is to have 0.2 millimeter crack width. So you see here, they are all stopped at 0.2 millimeter cracks with of the tensile phase. Then we put the pre-cracked specimen in the sustained load setup. As you can see here, we applied the same load with the load cell. Then we stop when the load is approaching the pre-cracking load. Then we fix the setup with the brown nuts. Then we move the load cell to produce all the specimen. After we also took some measurements for the crack width before and after the exposure. This is the pre-cracking. Then we put them in the exposure. You see here the amount of the specimen. I have to highlight here that we used 3 containers. One is for the fresh water, the other one for chloride, 3.5% of NaCl, and the last one is with the geothermal water brought from the geothermal plant. Then here, this is the result of 6 months. We are continuing doing the research up to 1 year, hopefully. But this is the result of 6 months. We see here the resonant frequency test. You see at the 0, the pre-crack one. Then after 1, 2, 3, and 6 months, we saw some recovery and also gaining of the dynamic elastic modulus for flexural and axial one. Also the UPV, we saw also some consistent recovery. Also for index of stiffness recovery, we use this equation for the stiffness of the pre-crack and after the loading, after the exposure. We see some recovery up to second month. Then after third and sixth month, the recovery rate decreased. And here you can see there is a creep effect intervening. Actually, now we have to figure it out how to quantify this because we saw that magnetizing exaggerated at the 6th month. Then for the 9 or 1 year, we will see how to quantify this this effect. Then we also brought some slabs to the lab to do one-way and two-way slab system to represent the second and the third basin behavior. You can see here the long slab presenting the second basin and the small slab presenting the third panels. You can see here the failure mechanism of the two slabs. Here we are doing some model. For the slabs, we started from constitutive law. We developed with the sustained load specimen. We did the sectional analysis, analytical model, nonlinear analytical model. We used the virtual work to link the section, the yield line, the sectional behavior along the yield line to produce the load deflection curve and compare them to the experimental ones. And we here see the comparison with regard to the long and the small slabs. They are showing a good, let's say, a good agreement. Then the main idea, we are coming back to the main idea, is to quantify the constitutive law under the sustained load and the mechanical exposure together to do to extract the exact constitutive law by inverse analysis. So we took the 4-point bending test from each specimen of these. We did the inverse analysis. This is for the X0 exposure, which is the chloride exposure. You can see here the red lines are the average of a specimen from each month. So the red circle is 1 month, then 2 months, then 3 months, then 6 months. Then you can see here the behavior as we saw previously. There is it was a good let's say a recovery index. Then it's stabilized after 6 and the 3rd month, maybe because of the creep. We will see later after the 9 months. This is the X0 exposure. This is the chemical exposure, geothermal water, and sorry, the first one was fresh water. This is chemical, and this is the chloride exposure. We took all of these constitutive law. The main idea is to start from the 4 bending point test. So we have all this data. We did the inverse analysis to extract the constitutive law. Then we go to the sectional analysis, including the constructibility, steel fiber, like you see here, how the steel fiber contribute to the constitutive law, and the durability, which is basically built in the specimen since they are exposed and the sustained and the chloride and geothermal water. Then we do cross-section analysis. Then we ended up upgrading to the structural level, which are the UHPC element or UHPC panels. And this is some sample we started doing now. So we start from the inverse analysis constitutive law. We put them in the model. We derive the displacement load for the panels that I showed you earlier. We see here that the first month, the blue one, then the 2nd, 3rd, and the 6th months, not even at the ultimate, but also at the beginning, at the elastic phase, there are good recovery. Keep in mind, this is a specimen are under sustained load. The sustained load is like 80% of the capacity of each specimen, the small beam, and also an aggressive environment of chloride and geothermal water. And even though the creep intervene in the third and the sixth months, but the recovery is still valid for the second, third, and the sixth months. We will continue doing that. On May, we will do the 9 months, and on July, we will do the 1 year exposure, and we will conclude the durability assessment-based design approach. This is all. I'm coming to the conclusion. I'm putting here some conclusion from the on-site measurement that we saw, that the overall project framework is intended as a pioneer study moving toward performance-based design approach, since it's taking scientific data from the laboratory and in situ observation from the sites of the full project, of the full scale structure. Then we saw, like, when we reduced the thickness of the wall from 10 to 6, even more to 3 centimeters, we didn't see any serviceability limited state problems regarding displacement, vibration, leakage, and so on. One observation we should mark is casting of the UHPC. If the UHPC is casting vertically, we should keep in mind that this casting should be made segmental casting, not one patch or more than 1 meter, to avoid the segregation of the steel fiber. The prolonged experimental campaign I'm showing you now, I showed you, and we are still doing it, showed a very durable material of UHDC. This UHDC has some nano material inside them, nano alumina and nano cellulose, also crystalline admixture to promote the self-healing, autogenous self-healing. Then the DAT concept that we are doing now, the durability assessment-based design, will provide a design criterion for to predict the surface life and in a more scientific and reliable way. This is all. Thank you for your attention. For updates and results for this research, you can visit the website here, www.uhdc.eu. Thank you all. I will be here for the question.